So now we want to discuss carboxylic acids and how they can be transformed into some other functionalities outside of acid halides, which is what I just showed you. We can actually introduce somewhat of a new-ish functional group called the anhydride. What's that? Well, it's sort of like changing your carboxylic acid into a very specialized ester. The mechanism for doing so is not difficult, but let's see what an anhydride looks like, and you'll kind of get an idea of what I'm talking about. Let's say I started with a carboxylic acid, and I introduced, let's say, the acid chloride we just learned to make in the previous lecture, and I heated it up a little bit. I can drive this reaction forwards by using the carboxylic acid as my nucleophile, and I actually don't need either of them to be charged formally. Why? Because the carbonyl of an acid chloride is very, very, very reactive, right? That carbon is extremely electropositive. Typically, acid chlorides and acid bromides don't need a formal negative charge because of their heightened reactivity. Because that carbonyl is so electropositive, it may as well be formally plus. So as such, you can kind of operate under the assumption that it is already activated. Think of acid chlorides as already being under acidic conditions. So our weak nucleophile, therefore, is going to be our oxygen here. These electrons are going to do a 1-2 addition. In and up. Down and out. The good leaving group is the one that is the chlorine, of course. Oops, I forgot my positive charge over here. And you're probably going to work up this reaction because the workup conditions are going to be basic. You could imagine that the chlorine minus grabs the H. That means you're generating HCl in the reaction. So either way you look at it, you're going to work it up under basic conditions to deprotonate or neutralize any HCl buildup. Like I said, either way you look at it, you form this new species. A carbonyl, oxygen carbonyl, is called an anhydride. It's a special term for maybe even a specialized ester, right? You can think of it as a carbonyl with an O carbon group. That's kind of like an ester, but it's a very special type of ester called an anhydride. The reason where anhydride comes from is because you're actually sharing this oxygen between them, and prior to, I think you can think of it as loss of water in some cases. These reactions, or the formation of an anhydride, originally worked between two carboxylic acids under acidic conditions. So instead of losing a chlorine, you'd lose a water when you heated this up and got these two reacting to form the anhydride. So loss of water without water is where the term anhydride comes from. But the most efficient way to make an anhydride is using one of them as an acid chloride. This gets the reaction going a little bit easier. But it's really just an in-up, down-out reaction. And there you go. I'll leave this one for you guys. You can practice how to do an intramolecular anhydride formation. And again, in this instance with heat, you can see that I'm using two carboxylic acids. The heat is what drives it forward to lose water. So it is a reversible reaction technically, but if you're driving it forward with heat and you're maybe distilling the water off as you go, you are taking control of Le Chatelier's principle to drive the reaction to form the anhydride. So just imagine that you've got lots of heat driving it forward to lose water, and instead of acid chloride, you're just going to lose water instead of chlorine. But I'll let you guys try it on your own. What else can we do? Well, we can convert carboxylic acids to esters, and we can do this forwards and backwards. So I'm going to show you both how to change a carboxylic acid into an ester, and I'm also going to show you that an ester can get converted back to a carboxylic acid. These are reversible reactions, hence the arrows, because the atom that we're adding, remember, we're driving on the alcohol, therefore we're going to drive off the OH. In the reverse reaction, we're driving on the water and we're driving off the alcohol. So it's the same reaction backwards and forwards. If we started with a carboxylic acid, under acidic conditions, I should really put in here, we should put in acid base plus 1,2 addition. Acid base plus 1,2 addition. The first step is acid base chemistry. Protonate your carboxylic acid, activate the carbonyl, after acid-base chemistry, we're now ready for our 1,2 addition. We look and see that we have a weak nucleophile because our electrophile is strong, right? Formal positive charge. So we just use our, let's say, ethanol as our weak nucleophile, and we're ready for the in and up. In up reaction. And at this point, I like to remind myself I'm driving the alcohol on. I'm driving the alcohol on. I'm driving the OH of my carbonyl off. It doesn't matter which one. I mean, they're both OHs, so drive one of them off. But to do so, I've got to, because under acidic conditions, I've always got to proton shift to make a better leaving group. Acid-base chemistry. So I'm going to shift it from the oxygen of the alcohol to the oxygen that was once the carbonyl. Doesn't matter which one you choose, they're both OHs. Now we're going to do down, out. Down and out. Now at this point, understand that we have a resonance structure. You could have done down out with the other OH. That would have probably been a quicker and smarter way to do it. I chose the other oxygen, but understand that there's resonance here. Right? And that's my ester. After workup, I have an ester. If I want to go back and change this ester back to the carboxylic acid, I can do that as well. I can drive my water on. So let me just show you here that I needed to keep I drove the alcohol on. If you look from start to finish, You can think of it, if you want to do it a little quicker, you can think of it as the Q group, right? The not carbon or hydrogen group that flanks your carbonyl is the group that you're getting rid of, right? So I ended up swapping that group out on you by mistake, but, right, you can see it maybe a little bit better. I drove off one of the OHs. All right, well, let's do this. I'm driving the OR off this time, and I'm driving the water on. Let me try to write it a little bit more simply. Let's say I started with this ester. I add an acid. I do my acid-base chemistry first to activate my carbonyl. Carbonyl activated, acid-base chemistry. I'm now ready for my in up. What am I driving on? I'm driving the water on. So the water is going to go in and up. Okay, so I'm driving the water on, and I'm driving the ester off. So let's keep that in mind. Let's keep the blue on and drive the yellow off. Okay, so we just did the in up. Now, because we're under acidic conditions, we have to proton shift. This is why the highlighting helps, because it helps you to realize where you're shifting your protons to. I'm shifting it from the blue to the yellow so that I can drive off what's in yellow. That's the group I'm driving off. The group I'm keeping on is the blue. So now I'm ready after my acid-base chemistry. And again, look what we've done. Acid-base chemistry, in and up. Acid-base chemistry, down and out. So take your pick. Doesn't matter which OH you use to do down and out. I can use the top one, doesn't matter. Down and out, and I am here. So I've just driven off the alcohol. I've kept the OH on, and I have my carboxylic acid. I'm now ready to just work it up and get rid of the extra proton. Under basic conditions, mild basic conditions. And I end up with my carboxylic acid. In, up, down, out. Here's a reaction for you to try. This is specifically a carboxylic acid getting converted to an ester. And when you do it intramolecularly, it's called a lactone formation. So when you have an ester that's part of a ring, like where the oxygen is part of the ring, then it is a lactone. So I'm going to let you guys try this one on your own as practice. Just notice that here's your carboxylic acid on the right-hand side, and your alcohol just happens to be attached to the same species. Okay, how about carboxylic acids to amides? Again, we can convert these to the amide. We can take the amide and convert it back to the carboxylic acid. I will, however, say that mechanistically, changing your carboxylic acid to an amide using straight out an amine and heat is not the best way to do it. Why? Well, again, you're adding a base, and bases want to react with the proton of the carboxylic acid. So it's just not the most efficient way. You need a little bit more heat to push this along, but I'll show it to you anyway, because it is an in, up, down, out. We're going to drive off the Q group. We're going to drive on the amine. And mechanistically, yes, the first step actually is acid-base chemistry with itself. And you're going to have a negative charge there, but let's just kind of skip forward and say, if I've got heat driving this forward and we do get to see some amide, what would this look like? Let's just skip the acid-base reaction with this hydrogen. If we could push it, then we would go in and up. Driving the nitrogen on, driving the oxygen off. Notice we're not using acid-base chemistry here. We technically are. We have an acid, we have a base. So, technically we are under acidic and basic conditions, but that's what the heat is for. We're going to shift a proton so that we can drive the OH off better. So shift it from the blue to the yellow. And you guys could do this if you, for all these mechanisms, if you keep what you're driving on one color and what you're driving off the other, then you know exactly where to shift your protons. Makes it a little bit easier to follow. Driving the nitrogen on, driving the now water off. Now we can finish. We did in and up in the beginning. We're now going to do our down and out. Down, out. And we have our amide and loss of water. Okay, so maybe that might be the best way for you guys to look about it. Just simply color code what you're driving on. The Q group is coming off, and it's just an in, up, down, out reaction. Notice here we have an amide, not a carboxylic acid. Amides are neutral. They are not acids. They are not amines either. They are an amide group. And so amides are neutral. You actually do need a little bit of oomph to get this going. Oops. So if I were to do the reverse reaction and start with an amide, I would start with my acid-base chemistry to activate the reaction. I now have an electrophile with a formal positive charge, so I can now add my weak nucleophile, which is water, driving the water on, removing the NH, the Q group. Oops. So in and up. So here we should add our acid-base chemistry. We got in and up. Can you see the repetition here? OH, OH2. We're going to drive the nitrogen off. We just drove the water on. So we want to proton shift to make our nitrogen the better leaving group. We drove the water on. We're driving the nitrogen off. The nitrogen's now ready to leave in our down out. So we can go down and out. This gets us to the nitrogen, whoops, the nitrogen being driven off, the oxygen been driven on, and I am now at the point where I can work it up to get my final product, which is the carboxylic acid. Acid base in, up, acid base down, out, work it up. Very, very repetitive. I do like highlighting what you're driving on and highlighting what you're driving off and being consistent in your color coding. It super helps keeping track of proton shifts. Just to give you guys a little bit of perspective here, this is exactly the chemistry in biochemistry, right? Peptide bond formation. In fact, if you think about how peptide bonds are made in the lab, if people want to construct boutique peptide chains, a lot of the times the chemistry we use is making a carboxylic acid into a better leaving group, like we saw with acid bromides, right? You can take carboxylic acid, react it with PBr3 and make a much better leaving group. This gives us a lot more control because now if we add an amine, right, and we want to form an amide, understand that that highlighted bond right there, that's a peptide bond. The peptide bond is just a specific bond in the whole functional group, which is an amide. And we just made amides in the previous slide. However, the best way to make an amide is actually to change your carboxylic acid into a better leaving group, like the bromide or the chlorine, and then react it with an amine to form your peptide bond. So we see this actually in biochemistry when people trying to make their own peptide chains. You can start with an amino acid. I have amino acid 1 labeled right here. And then what you can do is use this phosphate group with ADP, right? So the oxygen of the carboxylic acid port end of the chain does an SN2. ADP is the leaving group. It's another O phosphorus. So that leaves as ADP, right? Because it was ATP. Now it's leaving as ADP. And now you've got this big group that's going to be your better leaving group. So this whole system right here is your good leaving group. And what you're driving on is the amine of another amino acid number 2. So now when you do an in-up reaction, in and up, you get here. We're going to remember what we're driving off. We're driving off the phosphorus, we're driving on the nitrogen. So now when we go down and out, we have our new peptide bond, which I'm indicating down at the bottom. We've just formed an amide from a carboxylic acid. That's all it is. Make the carboxylic acid into a better leaving group, and then use another amino acid, the amine part, to be the nucleophile. And that's how you make a peptide bond. Do this over and over again, and you have a peptide chain. You can do these reactions intramolecularly as well. This is called a lactam. So when you actually form an intramolecular amide, it's specifically called a lactam. I'm not too concerned that you know these words. I just want you to know the mechanism. So for practice, under acidic conditions or heat, try making a lactam or reacting a carboxylic acid with an amine that happens to be connected onto the same species. Okay, our last reaction before summarizing is carboxylic acid reductions. Nothing new here apart from a little bit of uncertainty about the mechanism. Even if you look at the Klein book, it'll also talk about the uncertainties regarding this mechanism. But for all intents and purposes, we can write a reduction and just sort of wiggle our way through it, okay, using the 1,2 addition chemistry that we know. So what if you remember, I want you to recall that a primary alcohol can get oxidized under really strong conditions goes through the intermediary aldehyde, and it just keeps going and gets oxidized further to the carboxylic acid. What I'm asking is, can we take this carboxylic acid and go all the way back to the alcohol using reduction, H- conditions? And that's what we're going to show here. Now, the reason why the mechanism is a little dicey is because, again, the first step is clearly going to be, if we have an H- source like lithium aluminum hydride, acid-base chemistry is going to prevail. Right? We're going to have this problem, but despite that, we have to assume that there's some proton source around that can allow the oxygen to not leave as an O2-. That would be weird. So what I'm going to do is say, let's just ignore the acid-base chemistry that's probably happening so that we can write something a little bit neater. This is definitely happening, but it doesn't help us in the mechanism if we're trying to understand the reality, which is experimentally, we do see carboxylic acids being able to be reduced. So let's just do an in, up, down, out reaction. Notice I'm using arrows that go unidirectional in one direction, and that's because the nucleophile I'm adding is not going to come off, right? Once we put an H- onto a carbon, we're not popping that guy off. So we're going to just cut to the chase and do in, up. We already have a strong nucleophile / base. We're going to do an in, up. We're going to take off the OH. We've just added the H. And then we're going to do a down, out. Oops. Down and out. We are now at the aldehyde, the midpoint, and we know aldehydes are very susceptible to H-. We saw that aldehydes and H- in the aldehyde chapter can undergo reduction, and we also know that aldehydes are more reactive than carboxylic acids. So the next equivalent of H- is certainly going to react with the aldehyde. We can't stop this train. So we did in, up. We did down, out. And because we reformed the aldehyde that's still susceptible to H-, we're going to do another in, up. Can't stop the train. Can't do any more down, outs, right? We're stuck. Can't do a down, out. We've got a carbon, a hydrogen. We're done. We just have to work it up. So we've just formed our primary alcohol. Poorly written. Primary alcohol. So there you go. You can go backwards. You can start with a carboxylic acid and go back to the alcohol. Again, but totally bypassing the aldehyde that you made in the middle, because aldehydes are even more reactive than the carboxylic acid and are just going to continue. Lastly, let's take a look at where we've been. So we know now that if you look down at the bottom here, alcohols, right, down at the bottom, can get converted to their carboxylic acids. We just learned that carboxylic acids can get converted all the way back to the alcohol. We also have learned that carboxylic acids can be converted to acid chlorides. We've learned that they can be converted to anhydrides. We've learned that they can be converted to esters. And I showed you how to go from an ester back to a carboxylic acid. We can convert amides to carboxylic acids, and technically there's no arrow showing it, and that's because it's not efficient. Carboxylic acids with amines can go back to the amides as well, but they're not showing it because they're actually showing a much better way to do it. The better way to convert a carboxylic acid to an amide is a two-step process where they want you to first form the acid chloride, and then the acid chloride can form the amide. So they actually want you to go through the acid chloride because it takes out the protic system there from acid-base chemistry. But it's fine either way. It's just not as efficient. So we've covered a lot of these arrows. We don't have much left to do. And again, the trend is going to be in, up, down, out, in, up, down, out. Okay? So I'll end here at slide 19.